Okay, so let's look at using Ka to calculate pH of a solution. This is a common type of question you'll get about acids and bases in higher level. So let's start with number 1, propanoic acid. This is propanoic acid. It's basically a carboxylic acid, okay? When we study about organic chemistry, we learn more about these. Carboxylic acids are weak acids, okay? So in part A, give the equation for the ionization of propanoic acid in water and deduce the expression for the ionization constant Ka of propanoic acid. So let's answer the first part, which is the equation for the ionization of propanoic acid. So here it is here. You start off with propanoic acid. The formula is given at the top here. And then it's a reversible reaction. And all you do is you take off the hydrogen, okay, which is we've taken off this one here, and it becomes H+, and don't forget that the rest of this now has a negative charge because you've taken off a hydrogen which is positively charged, and there you have the equation for the ionization of propanoic acid, okay? And the second part is deduce the expression for the Ka. So Ka is the products at the top and the reactants at the bottom, okay? So simply it's this expression here, okay? Right, part B, calculate the Ka value of propanoic acid using the pKa value in the data booklet. So I looked in the data booklet and I found the pKa of propanoic acid to be 4.87. Now you should know that Ka is equal to 10 to the negative pKa. Okay, so that's what I've done down here. Ka equals 10 to the negative 4.87, which gives me this here, 1.35 times 10 to the negative 5. Okay, so that's parts A and B. Relatively simple. Now, part C is more challenging, so use your answer from part B to calculate the concentration of hydrogen ions, H+, in an aqueous solution of propanoic acid of concentration 0.0500 mole per decimeter cubed, and hence the pH of this solution. So what you need to do here is you need to have an ice box, okay? So it's helpful to write the equation at the top, okay? And then you've got the initial change equilibrium down the side here. So you know the initial concentration is this here in the question, 0.0500 moles per decimeter. And the initial concentrations of the CH3, CH2, COO negative and the H+ are 0.00. Now the change is negative X here. And because it's a 1-to-1 ratio, you have plus X here and plus X here. Now, for equilibrium, the assumption that we make is if you subtract X from this number here, 0.0500, it will be approximately the same to this number of significant figures. Okay, so the assumption we make is if we take X away, we basically stay with the initial concentration, which is why we're going to use this initial concentration in our equation, okay? And then for the other two, we have X and X, okay? So that once you've made your icebox and you need to input the values into the Ka expression here, okay? Just to remind you, this is what we did earlier. Now on the next slide, that there is my Ka, which I deduced in part B, okay? And we have X squared here, and this at the bottom is the initial concentration of the propanoic acid here. Now what you have to do here is solve for X, okay? Now to get X on its own, I've multiplied both sides by that, okay, which obviously cancels these two out here, and I obviously have to multiply that by the same on this side, okay? And then if you look down here, we end up with x equals the square root of this times this, which is 6.75 times 10 to negative 7. So you're solving for x here. And then if you do the math, you end up with x equals 8.22 times 10 to the negative 4. Okay? And that should be moles per decimeter. Okay, so this is basically the concentration of the hydrogen ions. Okay, so once you've done that, you have to obviously find the pH. Now you know that pH equals negative log of the hydrogen ion concentration, and you input this value here, which we just calculated, and the negative log of that gives you 3.09. Okay.